Hi students, here is a solution for your homework question from substitute frame method. The question is to analyze the frame for calculate the negative span moment at a beam BC. The moment of inertia of the beams is given as 1.5 times that of the column. Then total dead load is 14 kilonewton per meter and the total live load is 9 kilonewton per meter. The span length for beam AB is 6 meter, then BC is 4 meter, and again CD is 4 meter. Height of each column is given as 3.5 meter. So here is the live load position for getting maximum negative span moment at beam BC. So this is our substitute frame, and this is beam BC. The influence line diagram should be like this for getting maximum negative span moment at the beam BC. So that load is distributed throughout the beam ABCD, and the live load distribution should be like this. The beam under consideration should be unloaded with the live load, and the adjacent span should be loaded with the live load for getting maximum negative span moment at the beam BC. Here is the live load and dead load distribution for getting maximum negative moment for the span BC. The total load on BC is 14 kilonewton per meter. That is only dead load. Then span AB and span CD is loaded with the live load as well as the dead load of 9 kilonewton per meter and 14 kilonewton per meter respectively. The total load acting on span AB and span CD will be 23 kilonewton per meter. Then first step is to calculate the fixed end moments. So the beams are loaded with the UDL only. So the fixed end moment for beam AB will be minus WL square by 12, or when it is substituted with the values, it will be minus 69 kilonewton per meter. Minus 69 kilonewton meter, or 69 kilonewton meter in anti-clockwise direction. Then for the span BA, it will be 69 kilonewton meter. And similarly for other beams BC and CD, for BC it will be minus 18.67 kilonewton meter and positive 18.67 kilonewton meter for BC and CB. Then next span, it will be minus 30.67 kilonewton meter and positive 30.67 kilonewton meter for the span CD and DC. Here is the calculation of distribution factors for each and every members. Actually, we require only the distribution factors for the beams, that is marked in red color. For beam AB, it is 7 by 23 or 0.304, and for beam BA, it is 0.209. For beam BC, it is 0.313. Then for beam CB and for beam CD, it will be 0.284. Then for beam DC, the distribution factor is 0.396. This distribution factor table is already discussed in the problem number 2. This is the moment distribution table. So first row of the moment distribution table is join, and the second row is members. Then third row is distribution factor, fourth one is fixed end moments. For beam member AB, the distribution factor is 0.304 and the fixed end moment is minus 69. For beam BA, distribution factor is 0.209 and fixed end moment is 69. For beam BC, distribution factor is 0.313 and the fixed moment is minus 18.67. For beam CB, distribution factor is 0.284 and the fixed moment is 18.67. For beam CD, the distribution factor is 0.284 and fixed moment is minus 30.67. For beam DC, distribution factor is 0.396 and the fixed moment is 30.67. First of all, we are going to balance the moment at the joint AB. There is only one member loaded with the loading. So total moment acting at that joint is minus 69 kilonewton meter. So when it will be balanced, the balanced moment will be 69. Then it will distributed to their members at that joint according to their distribution factors. So balancing moment at member AB will be 69 into 0.304, that is 20.976. Then coming to the joint B, there are two members. So total sum of the moments at that joint will be 69 minus 18.67. Then it will be distributed to their members associated with that joint according to their distribution factor. So the balancing moment will be multiplied with the distribution factor, and balancing moment at joint BA is obtained as minus 10.52, and at BC it will be minus 15.75. Then coming to the joint C, and the total sum of the moments at the joint C is 18.67 minus 13.67, that will be minus 12. When it will be balanced, it will be positive 12 kilonewton meter. Then it will distribute according to the distribution factor. So for member CB, the balancing moment will be 12 into 0.284, that is 3.408. And same moment will be at the member CD, that is 12 into 0.284, that will be 3.408. Similarly, in the joint, at the joint D also, the balancing moment at joint at member DC will be minus 12.145. Then the moment will be, the balancing moment will be carried over to the far end according to their far end condition. So for member AB, the far end will be B, that is a intermediate joint, which is considered as a fixed end. So half of the moment of moment from AB will carry over to the joint BA. So half of the moment 20.976, that is 10.488, will be carry over to the member BA. Then next member is BA. For BA, the far end is A. Then half of the moment, that is half of 10.52, half of minus 10.52, that is 5.26, will be carried over to the far end. Similarly, for other members also, the moment will be carried over to the far end. Then again balance the moment. We have to conduct minimum 2 cycle moment distribution. So there will be one more step to calculate the balancing moment and the carryover moment. Then add the moments for getting the getting the moments of beam BC. So final moment of BC is obtained as minus 13.551, and for CB it will be 16.253. For BC it is anti-clockwise moment, and for CB it is clockwise moment. Here is our final results. For beam BC, on the left side of the beam BC, the moment obtained was 13.551, 34.551 kilonewton meter in anti-clockwise direction. On the right side, it is for 16.253 kilonewton meter acting in clockwise direction. Total load acting on the beam is 14 kilonewton per meter. So this is our bending moment diagram. So first we are going to draw the free bending moment diagram. Free bending diagram can be drawn by considering the supports as simply supports. So maximum the shape of the free bending diagram will be parabola because the load acting on the beam BC is UDL. So maximum load acting, maximum moment is obtained at the center as WL square by 8, that is equal to 28 kilonewton meter. The next one is the fixed bend diagram. So this trapezoidal shape is our fixed bend diagram. On the left side, the value of fixed bend diagram is 34.551 kilonewton meter, and on the right side is 16.253. So average of this fixed bend diagram will be at the center, that is 34.551 plus 16.253 all divided by 2. This will be the average of fixed bend diagram. So we have to calculate the maximum negative moment on BC. So that will be at the center. So maximum negative moment will be the difference between free bend diagram and a fixed bend diagram. That is, this value will be the maximum negative moment at the center. So that's equal to 28 minus average of fixed bend diagram, that is 28 minus 34.551 plus 16.253 by 2, that is equal to 2.598. Actually this is hogging moment.